Hi everyone. So in our last video, we introduced exponential functions and looked at what their graphs look like. So much like what we've done with other types of functions, in this video, we're going to focus on drawing transformations of exponential functions. So before we get into the transformations, I just want to remind you what the general shape looks like for exponential functions. So this is probably the most important piece of information from the previous video. So remember, an exponential function is any function of the form f of x is equal to a to the x. The only restriction is that this number a, which is called the base of the exponential function, it can't be a negative number, it can't be 0, it can't be 1. So we talked about in the last video why that was, but any other number will work as the base for an exponential function. And so what we saw in our last video is that there's two different general shapes that you're going to get for an exponential function. And those two shapes are going to depend on whether that base number is greater than 1 or less than 1. So on the left, we have the shape that you'll have if your base is greater than 1. So if that's your base, then your function is going to increase from left to right. It's going to have a horizontal asymptote on the left side at y is equal to 0. And then on the right side, it's just going to go up and up and up and get steeper and steeper. Whereas if that base is less than 1, well, then your function is going to decrease from left to right. So it's still going to have a horizontal asymptote at y is equal to 0, but that horizontal asymptote is now going to be on the right, and the function is going to increase and increase and increase on the left. So we went into detail about why that is in the last video. So if you want to remember why these shapes look the way they are, I would go back to the last video for a detailed explanation of that. Other thing I want to point out is that for any exponential function, the y-intercept is always 0, 1. And that's because if you have an exponential function, if you plug in 0 for x, any number raised to the 0 power is always equal to 1. So you're always going to get that y-intercept of 1. Okay, so let's get into some transformations. So this first set of examples are all going to be transformations of 3 to the x. So we're going to start by just sketching the graph of 3 to the x so that we have that as a reference when we go in to do the transformations. So 3 to the x, we did this one in the last video. As we mentioned, it has a y-intercept of 0, 1. And then we really just want to plot a couple more points to be able to draw these transformations. Just like with other transformations we've done, you don't want to get caught up on doing too many points. If you have just like 3 points and then you know what the general shape looks like, that will serve you well in doing your transformations. So another key point would be when you plug in 1, you would get 3 as your output. So we have the point 1, 3. And then when you plug in 2, you would get 9 as your output. And then you could also calculate some points over here on the left, but I think these are going to be the easiest 3 points to work with. So I'm going to connect them like this, and the graph is just going to get steeper and steeper and steeper as it goes. And then on the left side, we have this horizontal asymptote, right? So the graph is going to approach. It's never going to actually touch the x-axis, but it's going to get closer and closer as it goes out to the left. And so we have a horizontal asymptote, as we mentioned, at y is equal to 0. So again, these are the points we're going to focus on. I'll just label them. So we have 0, 1, we have 1, 3, and we have 2, 9. Okay, so let's take a look at some of these transformations. So first one I want to do is on the left. So g of x is equal to 3 to the x minus 1 plus 2. So And by the way, I would encourage you, as we do these examples, to pause the video and try to figure out what these different transformations are. And then you can even sketch them yourself and come back and see whether you sketched it correctly. But I would at least pause and see if you can state in words what the transformation is going to be. So in this example, we see that we're doing two different things. We're subtracting 1 from x, and then we're also adding 2 to the function as a whole. And so remember, anytime we're adding or subtracting, that's always going to be a shift. So if we're adding or subtracting from x, that's going to be a horizontal shift. And horizontal shifts go kind of backwards of what you would expect. So this one is going to be a shift to the right by 1. And then we also have plus 2. And so that's being added not to x, but to the function as a whole. And so that tells us it's a vertical shift. And specifically, vertical shifts go kind of the direction you would expect they do, so +2 will go up 2. Okay, so what does that mean in terms of sketching our graph? That means that all of these key points that we identified, we want to just move them to the right one and up 2. So the original point we had was at 0, 1. So right 1 up 2 would bring us to now being at 1, 3. So that's the point that was originally the y-intercept on the graph. So next we have the point 1, 3. If we move that over 1 up 2, so 1, 3 over 1 up 2 is now going to be at 2, 6. And then finally, we had the point 2, 9. If we move that one over 1 up 2, that's going to be at 3, 11. So we want to plot the point 3, 11. Okay, so that gives us an idea of kind of the right side of our graph. So I'll connect these dots. What about the left side? So we need to make sure we're aware of the horizontal asymptote. So not only do you have to keep track of where your kind of key points you're focusing on ended up, but you do also need to keep track of where the horizontal asymptote ended up. So if we took this whole graph and we picked it up and moved it to the right and then also up 2, what does that mean about where the horizontal asymptote should end up? Well, the horizontal asymptote should be moved up 2 as well. Right? If we take this whole graph and pick it up and move it up by 2, it would make sense that the horizontal asymptote would also go up by 2. So I'm going to go ahead and put that in here. So our horizontal asymptote will now be at y is equal to 2 instead of at y is equal to 0. And then from here we can just do the shape of the graph the way that we know it goes. So let it kind of slowly get closer and closer to that horizontal asymptote. Okay, so next up we have this one. So this is 2 times 3 to the x. So before we look at how to do this as a transformation, there's one thing I want to point out that is a common mistake that students can make. So it's tempting to look at 2 times 3 to the x and be like, oh, I think I can simplify that, right? That should equal 6 to the x. However, that is just not true. So how can we really demonstrate to ourselves that that's not true? Well, let's pick a number for x. So for example, let's say you're doing 2 times 3 squared. So 2 times 3 squared, according to order of operations, you should do 3 squared first, right? Exponents come before multiplication. So 3 squared is 9. So we have 2 times 9. And 2 times 9 is 18. So that is the true value of 2 times 3 squared. If we tried to do it instead as 6 squared, we would get 36, which is a completely different answer than what it should be. So it basically comes down to order of operations, right? Order of operations says exponent comes first, then you multiply by 2. And so that's why you can't multiply that 2 in first. That would disrupt the correct order of operations. Okay, so that being said, now let's focus on this function and think about what is the transformation that is happening here. So in this case, we're multiplying by 2. We're not multiplying x by 2, we're multiplying the function as a whole by 2. And so what kind of a transformation is that going to be? Well, multiplication is always going to be a stretch or compression. If we're multiplying the whole function, it's going to be a vertical stretch or compression. And in this case, it's going to be a vertical stretch, right? Vertical stretches and compressions kind of work the way you would expect. So if we're multiplying by 2, it's going to be a vertical stretch by a factor of 2. In other words, all of our y coordinates are going to get multiplied by 2. Okay, so what is this going to look like in our graph? Well, we want to just take each of these key points that we identified in our original function and just multiply the y coordinates by 2. So instead of having the point 0, 1, we'll have the point 0, 2. Instead of having the point 1, 3, we'll have the point 1, 6. And then instead of having the point 2, 9, we'll have the point 2, 18. So this is what the right half will look like, and I'm probably going to struggle to draw this because it's very, very steep. There we go. All right, what about the left-hand side? What about the asymptote? So has the asymptote moved? Well, think about how stretches work, right? Stretches are like you're taking the graph and you're kind of pulling it. And so if you remember from other transformations we've done, whenever you have a point that is on the x-axis, it's not going to change when you do a vertical stretch, right? It's going to stay on the x-axis. And the reason for that would be if a point is on the x-axis, it's still going to have a y coordinate of 0 because 0 times 2 is still 0. So even though we, in the case of this horizontal asymptote, we don't have points that actually lie on the x-axis, it's still going to be true that that horizontal asymptote is going to stay where it is. Basically, because if you take, a horizontal asymptote like y is equal to 0, if you multiply 0 by 2, it's still 0. Whereas in this other example, why did the horizontal asymptote change in this example? Well, that's because we shifted, right? We picked everything up and moved it. So if you take y is equal to 0 and add 2 to it, it does change. Whereas if you take y is equal to 0 and multiply it by 2, that's not going to change. And so our function, our horizontal asymptote is still going to be y is equal to 0. And the only difference is that the graph is going to take a little bit longer to kind of flatten down because all of the points on this left side have been multiplied by 2. So it's going to be a little bit taller initially, but it's still going to eventually flatten down towards y is equal to 0. Okay, so let's do another one. So next up we have k of x is equal to 3 to the negative x. So what kind of a transformation are we looking at for this one? Well, we see that we are applying a negative sign, and we're specifically applying that negative sign to x. And so we know that when you apply a negative sign, it's going to be a reflection. And if you're applying that negative sign to x, it's going to be a horizontal reflection, meaning it's going to reflect over the y-axis. So basically what that means is that all of the points on our original function, the x coordinates are going to become the negative of what they originally were. So instead of, 0, 1 is going to stay where it is, right? Because 0, the negative of 0 is still 0, but 1, 3 is going to become negative 1, 3, and 2, 9 is going to become negative 2, 9. So we still have 0, 1, but now we have negative 1, 3. Oops, let me do this in a different color. We have negative 1, 3, and we have negative 2, 9. And so the graph is kind of going, it has the same shape, but it's just flipped, right? So it's like this. And then on the right side, it's going to flatten out towards the horizontal asymptote just in the other direction from where it normally would. So the horizontal asymptote did not change, right? It's still at y is equal to 0. So one thing that you might notice here is that this actually looks a lot like a graph that we saw in the last video. In fact, it's the same graph. So in our last video, we graphed 1/3 to the x. And if you recall, 1/3 to the x looked exactly like 3 to the x, but reflected over the y-axis. So the graph of 1/3 to the x looked just like this. So I want you to think for a moment, like, why do you think that is? Like, why do you think it's true that y is equal to 1/3 to the x and y is equal to 3 to the negative x are the same function? So just pause and think about that for a second. Like algebraically, how can you tell that those are actually going to be the exact same function? So remember how negative exponents work, right? So we talked about in the last video some kind of exponent properties. And so we talked about how if you take a number and raise it to a negative exponent, that's the same thing as taking the reciprocal of the base, so rewriting it as 1/3 and raising it to the positive power. So it's really just because of the properties of exponents that there's kind of just two ways of writing this function. So you'll see it written both ways. I think this is actually a slightly kind of more common way of writing this function, but it can be written either way. So just be aware that with exponential functions, because of this kind of fact, there's always going to be multiple ways of writing down the same function. Okay, so next up, last one that we're doing with transformations of 3 to the x, we have negative 3 to the x. So one thing that you might be thinking here, you might be thinking, well, I thought that we're not allowed to have a negative base, right? We talked about in the last video, you can't have an exponential function with a negative base. But that's actually not what's going on here. So negative 3 to the x does not mean the same thing as negative 3 to the x. So what's the difference? Well, it's actually pretty much the same thing we discussed up here. So it has to do with order of operations. So what is negative 3 to the x, the one on the left? That means that you're taking 3 to the x, you're doing this part first, and then you're applying a negative sign after. Whereas this one would mean that you're taking the number negative 3 and you're raising it to a specific power. So in this one, you're doing 3 to the x, then making it negative. This one would be taking negative 3 and raising it to the x. And so we already know that this is not an exponential function, right? We know that that's not allowed for exponential functions. But the one on the left is totally fine. It's just a transformation of an exponential function. So specifically, what kind of a transformation are we looking at here? Well, if we're applying a negative sign to the function as a whole, we know that that is a vertical reflection, or in other words, it's a reflection over the x-axis. And so what that means is that if we look at our original function here, instead of, in the last example, we flipped the x coordinates. This example, we're just going to flip the y coordinates. So all of the x coordinates of these 3 key points are going to stay the same. We're just going to flip the y coordinates. So instead of having the point 0, 1, we're going to have the point 0, negative 1. Instead of having the point 1, 3, we're going to have the point 1, negative 3. And instead of having 2, 9, we'll have 2, negative 9. And so this part of the graph is going to go down like this. And then we're still going to have the same horizontal asymptote, right? Because we didn't shift anything around. It's really only vertical shifts that are going to change the horizontal asymptote. So we still have a horizontal asymptote at y is equal to 0. The only difference is that now instead of the graph kind of getting closer to the horizontal asymptote from above, now it's approaching it from below. So this transformation is very different from a typical exponential function, because we talked about in the last video how for an exponential function that has not been transformed, its range is just going to be all numbers bigger than 0. So when we do this reflection, actually the range would be all numbers smaller than 0, right? We can never get a positive output from this, and that's because this portion is always going to be positive, right? 3 to the x, no matter what you plug in, you get a positive output, but then you apply a negative sign, and so that forces the whole thing to be negative. Okay, we're going to do just a couple more examples. So these were all different transformations of 3 to the x. We're now just going to do a couple more that are transformations of different exponential functions, just to get a little bit more practice. So first example we're going to be looking at is 1/2 times 4 to the negative x. So we're going to have to apply multiple transformations to this. So first of all, what is kind of the basic exponential function that this is a transformation of? Well, it would be 4 to the x, right? That's kind of the base function that we can compare this one against. So let's start by graphing 4 to the x. So 4 to the x is going to go through 0, 1, like every exponential function. If you plug in 1, 4 to the 1 is 4. And if you plug in 2, 4 squared is 16. So we got a very steep exponential function. So one thing we talked about in our last video is the bigger the base of your exponential function, the steeper the graph is going to be. But it's still going to have a horizontal asymptote at the same value. So we're still going to have this horizontal asymptote at y is equal to 0. Okay, so that would be the function f of x is equal to 4 to the x. And so what we're looking at is 1/2 times 4 to the negative x. So we need to figure out what those different transformations are. So first thing, again, I just want to quickly mention, it would not be correct to say that this was the same as, we can't multiply that 1/2 in, right? So it would not be correct to say 1/2 times 4 to the negative x is equal to 2 to the negative x, right? We talked about that in the last example that was like this. So that 1/2 does not get multiplied in. What that 1/2 does is it's a vertical stretch or compression, right? Because it's multiplying the function as a whole. And so in this case, it would be a vertical compression, right? Because we're multiplying it by 1/2. So that means that the y coordinates will all get multiplied by 1/2. They're going to become, the whole graph will become kind of smushed, right? It'll become shorter. And then what about this negative x? Well, when we're applying a negative sign to x, that means that it's going to be a reflection, a horizontal reflection, right? So a reflection over the y-axis. So we have multiple steps going on, but because one is horizontal and one is vertical, they're not going to really affect each other. So we can do them actually at the same time. So what we're going to do is we're going to take each of these points that we've identified on our original function. We're going to multiply the y coordinate by 1/2 to get that compression. And then we're also going to flip the point over the y-axis in order to get the horizontal reflection. So the point that was originally at 0, 1, that's going to go down to 0, 1/2, right? If we multiply the y coordinate by 1/2. And then that one is not going to go anywhere when we do the reflection because if we multiply the x coordinate by -1 or try to flip the sign, it stays 0. Then we have a point at 1, 4. If we multiply that by 1/2, that will go down to being at 1, 2. But then we also have to reflect it over the y-axis, so it'll actually end up over here at -1, 2. And then finally, when we have this point at 2, 16, if we do the compression, that will bring it down to 2, 8, but then we reflect it over the y-axis, and so it ends up at -2, 8. And so now we can just connect the dots, and we end up with something like this. So in this case, again, the horizontal asymptote stays at the same place, even though the graph is approaching it from the other side or on the other side. Okay, last example. So this one is going to be -1/3 to the x minus 2. So for this one, let's start again by sketching our kind of basic functions. What would be the basic exponential function that this is a transformation of? Well, it would be 1/3 to the x, right? So let's start by sketching that graph. And we're going to sketch it down here just because of how the axes are set up. So because this one is going to be a reflection over the x-axis, it just would have been kind of difficult to fit them both on the same graph. So we're going to graph them separately. So here we're going to graph 1/3 to the x. We already did this one in our last video, and then we actually did it today, right? When we did 3 to the -x, that was the same. So this one goes through 0, 1, it goes through -1, 3, and it goes through -2, 9. So this would be the graph of, 1/3 to the x. And then it has a horizontal asymptote to the right. So horizontal asymptote at y is equal to 0. So this would be the graph of f of x is equal to 1/3 to the x. Okay, so now we have to figure out what kind of transformations we're looking at in this example. So as we just mentioned, we have this negative sign out in front of the function, and so that tells us that we have a vertical reflection, right? Or a reflection over the x-axis. That will give us a vertical reflection. And then what else is going on? Well, we're subtracting 2. We're not subtracting it from x, we're subtracting it from the function as a whole. So that tells us it's a vertical shift. Specifically, it's a shift down by 2. So it would be possible to do this all in one step. The important thing to remember, though, is with order of operations, we have to do the reflection first, then the shift. I think that this one might be a little easier to do it in steps. So let's start by doing the reflection, and then we'll do the shift separately, just to kind of make things a little less confusing. So for the reflection, all we're going to do is take these 3 points and flip the y coordinate to being negative. So we're going to have the point 0, -1. We're going to have the point, instead of -1, 3, it's going to be -1, -3. And then instead of -2, 9, it'll be -2, -9. So it'll be like this on the left, and then on the right we'll have the horizontal asymptote, but it will be approaching it from below this time. So this would be the graph of y is equal to -1/3 to the x without the shift. Okay, so what else is going on here? Well, we also have a shift down by 2. And so if we want to shift this down by 2, what that means is that all of the y coordinates are just going to go down by 2. So the point that was originally at 0, -1 will now be at 0, -3. The point that was at -1, -3 will be at -1, -5. And the point that was at -2, -9 will be at -2, -11. And then what else will change? Well, because we shifted the graph, because we picked the whole thing up and moved it, that will actually change the horizontal asymptote. So the horizontal asymptote is going to go down by 2. So we're going to have y is equal to -2 as our horizontal asymptote. So this part of the graph is going to go kind of down and down and down and get steeper and steeper, but the right side of the graph is going to approach our horizontal asymptote. And so this blue graph is our final answer. All right, so that is it for this video. And please check out the worksheet to get some more practice with doing these yourself. And I'll see you all in our next video.